So we have three presentations for today. The first one is Network Service Interface Gateway to Future Network Services by Radoslav Szawania. Especially practicing my Polish there. He'll give us an overview of NSI and introduction to the concepts. The second presentation will be NSI client for VLBI by Paul Boven. And thirdly, we'll have Jeroen van der Ham will talk about the topology within the NSI, so the topology challenge. Before we launch into this, I'll just introduce myself. So I'm Guy Roberts, and one of my hats is as a co-chair, and we have another co-chair here actually, Tomohiro Kudo-san at the front, of the Open Grid Forum working group. This is called NSI. So NSI comes out of, is brought to you by the Open Grid Forum. If you're not familiar with OGF, it's a standardization body. It's an open standardization body with emphasis on grid-related aspects. And we have an infrastructure division in there where we're doing networking, solving networking problems. Without further ado, I think we'll move on straight into the first presentation. Radek, please come up. So I'd like to introduce Radek. So this is Radek Szawania. Radek works for PSNC, which is the supercomputing center based in Poznan.
Yes, right. In Poland, Poznan.
Radek is also the leader of one of the giant research activities, which is called hybrid network provisioning. And Radek is also a very active member in our group in the Open Grid Forum. Radek, over to you.
Okay. Okay, so after a short introduction, I just say my name in Polish, which is quite similar to what Guy say. My name is Radek Szawania. I'm working at PSNC and also in the Giant project. The hybrid blah 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 something is in fact the developing of the Autobahn tool, which is probably more familiar name for us, and also the bandwidth on demand system in Giant. So maybe that say a little more than the name of the task actually. Okay, so there's quite a list of the authors of this presentation, because there's a high number of people that are really involved in what I be saying here about the network services interface. There's a slide about the organization that is involved in that, but it's just give an overview of the interests of the people around this kind of a topic. So first thing is problem statement. So the case is that there are users that are completely unfamiliar with the network. They don't know anything about it. They don't know local administrators. They have never needed to contact anyone to do anything for the network. And suddenly they want to have resources that are far, far away in US or in China, Japan, whatever. And now they face the problem to set up a circuit, a connection that is usually a high bandwidth connection for a specific period of time. And they are completely out of their mind how to do that thing, who they should contact, who to call, send an email or whatever. And this is quite a generic problem. It happens every day, actually. I don't expect any kind of chemistry guy or physician to know how to deal with the network at the local level and international operators, how to contact, who to contact, how to set up a circuit, what is the capacity, etc. But the situation is there, and the people are facing this problem. So the NSIs will try also give an answer to that. There are already some systems that are trying to solve this issue, but they have some constraints that we want to get rid of it. So there are some systems that are restricted for single domain use, or they can operate in multi-domain environment, like Autobahn, for example, but they are restricted to the same system. So if you have two domains, you need to have Autobahn operating domains to enable talking between them and set up reservations. There are some different technologies. So one domain can be Ethernet domain, the other one can be SDH, the other one is IP. And the tools are usually strictly connected to the technology that the domain is using. So they cannot switch simply, cannot be installed in different domains and work naturally. The same applies to the vendor products. If you have a network resource management tool that is provided you by the vendor, it's usually attached to the hardware that you buy. And they not only is for the specific technology, but also for the specific equipment. So it doesn't mean that anyone can use it. For example, if you have the same technology and your neighbor has also the same but different vendor, this will not work. So what the NSI is proposing is to have, let's say, another logical layer above of that to deliver a single global network provisioning interface for all kinds of resources. It's not restricted to the network. I will say it a little bit later on that. The unified interface means that anyone can use it, and you can attach to any kind of a tool, any kind of a technology, any kind, whatever you have in your domain. If you have your microwave oven and you want to have it in NSI, you can do it. It's a unified way to do that, and you can force your meal to be ready before you come home. This is the overview of what is the interest and how people are interested in the NSI around the world. So as you can see, there is partners from Europe, from the United States, Japan, Korea. There's a lot of people that have an experience with the provisioning tools, provisioning system, and the networks, and they also deal with users. Also, users itself are also present in the NSI working group, so we get the requirements from them directly. As you can see, the map is covered, so the whole world is looking for something that provides us the unified, a single way to request the resources at the global scale. That slide is just clarifying the problem that people may have while talking on the NSI. The NSI network services interface in general is a framework, it's a very generic thing that is dealing with any kind of resources at the multi-domain level. And this can be anything. We in the NSI working group were focused by now on the connection service. So the NSICS is the NSI connection service, and this is the presentation is mostly about this kind of services. This is the protocol that we define for reservation of the bandwidth. So to create a circuit across the whole globe, multi-domain stuff, multi-technology in heterogeneous environment, trying to solve a global problem of the users that don't know how to approach the network, and also to introduce the dynamic provisioning, which is very important for us. There was a case recently in PSNC when we want to set up a connection from Poznan. That was either to Chicago or Louisiana, not sure right now. And I asked Glyph people in Netherlands to set up the circuit. The guy in Poznan sent the file faster through the regular internet in 2 days before the circuit was ready. So it took longer to set up a circuit than send a file through the internet, even if that takes 2 days. So there is a need for the dynamic services to set up a circuit that is created for a specific period of time, just to push the data very fast and close the circuit after that. The architecture is not very complex for that. Of course, there's an agent. There are two types of the agent, but in some cases they are merged together. It's a requesting agent that's to request the secrets, and provider agents that is managing the domain actually. And they build a topology, which is kind of a representation of the data plane in the control plane level. So in fact, they build some kind of a tree or a graph that they can communicate later for requesting the resources from the neighbors. The implementation is quite simple, actually. In fact, this is the WSDL file that defines the API. It's based on the document that was released under the OGF flag, the version 1 of the NSI connection service. It's publicly available. You can download it from a OGF page. The WSDL can be then translated into web service interfaces, and web service interfaces are quite flexible, so you can deploy that actually on any kind of a platform, any kind of a language. So whatever tool you have in your domain, you have an opportunity to deploy the NSI at the top of it. So we already did that for several implementations as an example, but there is no limitation actually. If you are able to deploy the web services on your tool, even if it's in a Perl script or in a bash in Linux, if you can set up a web service interface, you can actually add the NSI interface, enjoy the NSI cloud to exchange information about the topology resources, and make a reservation through your domain as well as the others. So that's the one of the most important things of the NSI, the unification of everything. The first version of the NSI provides just a simple, let's say, method or primitives for managing the circuit. So in fact, you can request the connection, explaining the endpoints, pointing out from where to where you want to get your connection. You don't care about the topology at all. You just need to know the endpoints, and the NSI will, and the corresponding system will do the rest instead of you. The reserve is actually the command that is coming from the end user or the application that is requesting the circuit. Then you can reserve the circuit, so actually book the resources for the future use if you want to have your reservation ready for the next week because you have a huge data transfer and you know that you will need a 1 gig connection from, let's say, Europe to US next week on Monday at 2 p.m. You can book those resources at that time, and the circuit will be provided to you at the specific time for a period of time that you requested. Then you can, there is a provision, so actually you configure the circuit, you get the resources ready for the transfer, so that's in fact happening in a week at the 2 p.m., as I mentioned before. You can release it, so if you transfer the file, you don't need it anymore, you can tear it down. And there is, in addition to that, there is a terminate request, which is canceling and clearing the reservation at any time. This is mostly for security reason or clearing up the system for the problem. The picture behind me also shows simplified state machine that is created for the protocol. It doesn't look very difficult, but still we are working to make it better or even simpler. That's the simplified because the full view of the state diagram, if you add all those transition state and the messages that are passing through, would not fit on a single slide. So this one looks very simple. In fact, the machine is a little bit complex, and we're still working to improve it to make it more easy to implement and the reward. So I would simply get through the example of how we set up a circuit in a multi-domain environment. We have a PC and some kind of video resources. There are 3 domains, completely independent. They use different technology, different tools, management system, different administrator policies, security. Everything is completely different. Each of those domains have the NSI agent that is over the system and is able to exchange information between domains with respect to the security policies and administrative policy of all those domains. So the users it's on the left side, sends the reserve request. I want a connection from my endpoint to the other endpoint. It goes into the initial state in the first domain. And now the first domain is the one that is responsible for setting up all the circuit all the way. So it's the first one on the path, on the topology. His responsibility is to check his own resources because we don't want other domains to look into the resources of other one. We want each domain to be completely independent and is taking care of his reservation internally by his own. So the first domain is checking if he has resources to fulfill his part of the reservation. We call this thing a segment. If he finds a way to provide those resources, he is forwarding the request to another domain. The another domain is doing exactly the same, just to confirm that the resources is there. If it's fine, then the request is forwarded to another domain. And the last domain is doing exactly the same thing. If all the 3 domains found resources to provide a circuit, so there is no way, there is a way that the circuit can be provided to the end user. The domain is confirming that green light for the reservation, and also they are booking the resources for the circuit. So since that moment, the reservation is actually able to be provisioned at the specific time, and there is no way that the resources can be used by other systems. at the specific time when the user wants the reservation to be ready, so it's the Monday 2 p.m., the reservation goes into the scheduled way. There's a little alternative way for doing that, but I would just focus on the simple case. It goes to the scheduled state. So the circuit is ready to be physically provisioned over the network. And the user can send a provision request command to force all the system to configure the network to be physically available for the end user. And when all the segments are configured, the information is sent back to the user that you have your circuit available and you can do whatever you want to do with the network. So the only thing you need to know is to know the endpoints, the start and the endpoint for the reservation. And this kind of things needs to be put in a, let's say, a topology or kind of a lookup service that is available for the end users. All the rest is done by the protocols and the tools that are below the system. Short view on the history of the NSI connection service. The first version of the protocol, the connection service protocol version 1.0, was released in August 2011. So actually it's just a couple of months ago from now. In September 2011, so actually 1 month later, we have a 6 independent implementation of the NSI protocol that were operating on a different tools, the network management tools that were deployed operationally in different domains. For the demonstration purposes at the Cliff meeting, we just use the control plane. So in fact, we bring our own notebooks and connect them into the network and exchange the control plane messages just to have a proof of concept that the control plane is working and we can exchange messages despite that some of those systems are Java-based, others are C-based, and they are managing physically different topologies. They can talk together and they can create the circuits over the physical networks. A month later, in October 2011, in Poznan, there was a Future Internet Week, we had another demonstration. We have more sites deployed, and they were physical. So we actually provisioned the physical connection between those sites, setting up the circuit, for example, from Poznan to Japan, to Tokyo, or any other kind of a configuration. And that physically worked. That was the first time the data plane was involved in the NSI protocol. The very big demo was in November 2011 on the SuperComputing. There was 9 sites involved and 6 NSI implementation, setting up the different part of the world, being able to set up a physical connection, transatlantic global level connections. That was the 1 gig circuits between each other, and to send kind of an information like ping or send a file or whatever, just to prove that the connection is there. This demo was presented on a few booths on the SuperComputing, at the IST booth, Pioneer booth, or Internet 2 booth, and the people just can play with the reservations and see how the things work. After that, in December 2011, having the experience of the demonstrations, knowing what is good and what needs to be improved, we released the version 1.1 of the connection service interface and started work on the version 2. In February 2011, we have 14 sites that has deployed the NSI. This is still a testbed topology, but it's based on a physical connection, so it's using the data plane. And we have, in the meantime, we have a few demonstrations at different occasions showing that this thing is really working and can unify the different system under the one flag of the NSI service, providing a global reservation across the world. So this graph shows more or less how the number of deployments was growing. Within actually 1 year, we have doubled the number of sites that was operating the NSI protocol and were able to exchange information and set up a circuit between others NSI in instances. Starting from 6 sites, we have at this moment 14, and more are expressing their interest to deploy the NSI. This is the current state, so the entrance, and it's your left side. There's the name of the tool that is using the NSI at this moment, have it implemented. On the right side, you have the entrance that is using that in this testbed topology. So you can take a brief view and compare how much of how much of work is already done on that. We know that the connection service version 1 is not perfect. We know what is missing, and we are already working on a couple of things that needs to be done to go further to the entrance and go to the production service of that. So there are a few more important things. This is the security. We need to enhance the security and security profiles for the communication. We need to improve the representation of the topology and the process of topology exchange or discovery of the protocol between the NSI instances. We need to work a little bit on the names of service termination point, which is actually the endpoints of the users, or service demarcation point, which is the exchange point between domains. We need to work a little bit on the error handling procedures. So if something goes wrong, we need to know how to behave to get rid of the problem, or to solve it, and to deliver the circuit to the users. We need to work on the firewall and NAT interoperability, so to assure that the communication between the NSA agents is always possible, and many, many more. There's a lot of things that we know that needs to be done, but we need to prioritize them. So the roadmap for OGF version 2 is simply that we identified the most important things in March 2012, so 2 months ago. We know what to focus on. We know how to deal with that. The target is July 2012 to release the document describing the new standard, the new version of the standard. We want to have in October 2012 a demonstration that is some kind of a alpha testing on the workshop, showing that the version 2 is working and confirm that. In November 2012 in Salt Lake City at the SuperComputing event, we want to have the let's say beta testing demonstration that is involving the sites of the NSI testbed, making a real circuits across the global circuits, sending the information, kind of a proof of concept for version 2 of the protocol. Probably at the end of the year, we also getting the experience from the demonstration. We also release version 1.1, so it's slight update on what's the definition of the standard. In 2012, there's also planned some production deployments. At this moment, I know about 4 deployments. At the end of this year, Nordinet, SurfNet, Starlight, and Pioneer Networks is planning to have the NSI running operational. This is mostly related to the Glyph automated goal infrastructure, not the regular NS infrastructure. Also, we have, at this moment, at least 3 users that expressed the interest in having and using the NSI protocol and setting up the global circuits using this tool. So about this topic, the next speaker will be talking a little bit more, providing the VLBI experiences on the NSI. So that's mostly all from my side. I just want you also to show if this thing will work. Okay. This is the, yeah, it's working. So this is the topology of the testbed that we have at this moment. On the right top corner, you will see the reservations that are set up in this topology. Below, you have the kind of a calendar that is showing the reservations on the particular ring. So at this moment, we have 1 active reservation, the blue one, and it's using the link between the it's cutting the screen, AST and the Starlight. I don't have a laser pointer, but anyway. Okay, so this is this reservation. You have the blue line here showing between which sides the circuit is set up. And this demonstration actually is not only a demonstration, it's also a kind of a test environment. This reservation is going continuously all the time, all day, all night, and the logs is tracking. So in case of any problem, we can immediately see what's happened, what's going wrong, and try to correct it and get an experience on what need to be improved on the CSI. Is it related to the NSI, or it's completely irrelevant? Or if it's related, then how can we improve the connection service to avoid this kind of a problem or solve them? So this interface is actually developing quite well, thanks to Tomohiro and the IST people. This one is using for showing the demonstration. The other interface you can also see at the Nordinet booth. It's based on the Google Maps view, showing the circuits going all around the globe. That's actually all from my side. I think I fit in time.
Well, thank you, Radek. That was an excellent sort of overview of the NSI concept, and also thank you very much for keeping to time. We have 2 minutes left for questions, which is perfect. And we have a question. Please go ahead. Yes.
Thanks. Yeah, just a small question for clarification, at least for me. As I understand, the NSI is maybe a combination of a user interface and something like a interdomain manager, as you connect several domains. As in Autobahn, you have a interdomain manager. Now you connect, let's say, super domains of certain underlying technique with each other and an user interface, so that the user can build the end-to-end connection. Is it correct? What I
it's more or less correct. You can understand it this way. In general, if you have the, let's say on a particular example, you have the domain that is managed by Autobahn. Let's say Jant is managed by Autobahn system. On the top of the Autobahn, you build the NSI interface. So it's just the interface. The logic is minimum at that level. Next to that, you have, let's say, SurfNet, and you have Dirac system managing this domain. You can set up the NSI interface at the top of them. Autobahn cannot talk to Dirac at all. They have different interfaces, different programming language, whatever. There are a lot of issues. The NSI is allowing those to communicate because they unify, they make an abstraction of the communication and the resources in both of the domains. So it's independent from the technology, independent from the representation. They unify that and enable that communication. So you can request a circuit going through Jan and then through SurfNet to the end user. So this is how it should work.
Did I see another question? Are you happy with that? No. Was there another question? Did anybody else want to raise a question? Okay, I think we're out of time.
Okay, thank you very much.
Thank you, Radek. Okay, so our next speaker is Paul Boven. Paul Boven works at Jive, where he is working with a team that are managing and building networks for the VLBI project. So Paul will talk about his development work on an NSI requester client. Paul.
Thank you. Hello everyone, my name is Paul Boven. I work at Jive in the Netherlands. Jive stands for Joint Institute for VLBI in Europe. So we're going to go through a lot of acronyms today. I'll explain most of them as we get along. Jive is over here in the Netherlands. What you see here is our central switch, and surrounded all over the world basically with radio telescopes, because what we do is radio astronomy. Radio astronomy, very long baseline interferometry, where we use telescopes that are on different continents very far apart to get the highest possible resolution images. So if you zoom in a little bit on this map, you can see places like here, Onsala in Sweden, or here, Jodrbank in the UK, for instance. And you see all these networking connections. Some of these connections are just routed. Most of them are actually both short distances, but also some of the very long distances around the world are actually light paths. And these light paths are the networking resources that we use for doing our observations. So what is VLBI? As I said, a very long baseline interferometry. The larger the distance between the telescopes, the smaller the details on the sky that we can see. And the more telescopes we have, the bigger telescopes we have, the better sensitivity we get. But also, very importantly, the sensitivity goes up with basically the square root of the bandwidth. So if you can record or send over the network 4 times as much bandwidth, we get twice the sensitivity to what's happening in the sky. So VLBI, as it happens at this moment, is usually running at 1024 megabit per second per telescope. So in a typical 8-hour observation run where you have like 10 telescopes participating, you end up with 40 terabytes of data. And this needs to be processed, and this is our correlator. This is basically a bespoke supercomputer with ASICs. And for a very long time, it was the fastest computer in the Netherlands if the only thing you wanted to do was take 2-bit numbers, multiply them, and add them. That's the only thing you can do. It's ASIC. It can only do one thing, but it was awfully fast at that. Nowadays, it's becoming a little bit of a bottleneck, and we can sort of replace it now. If we had a very large computer cluster, it would still take about 8 times as much electricity just to do the same calculations, and then we would only have the same capability. And what we're really looking for is to increase our sensitivity, increase the computing power, and one of the things we're doing for that is designing new correlators, for instance, based on FPGAs. The resulting data set after correlation is actually only a few gigabytes. What comes in is basically white noise, and there's lots of statistics done it, the cross-correlation function of it, and the result of it will actually give you an image. So when VLBI started, it started using this kinds of tapes. Actually, that's when it started at Jive. VLBI went much earlier, but this is when we started doing it in Holland. This kinds of tapes, which can actually already record at 512 megabit per second, maybe even 1024 if you're really lucky. Unfortunately, at those speeds, such a tape only holds like 15 minutes of data. And then the price of hard disk became much lower than the price of special purpose tapes. So we started sending around hard disk specs. These are 8 hard disks. There's a connector on the back. This pack goes into a machine. At the telescope, it gets recorded, it gets shipped to us. We play it back in a similar machine, and we do the high-performance computing that is needed, and then it goes back to the telescope again. So we keep sending those disk packs back and forth. We cannot afford to actually keep the raw data because we're talking about terabytes per experiment. We have a disk pool that's about 2 petabytes in size at the moment. And nowadays we're experimenting with VLBI, where we use fiber connections, light paths or routed connections to get data from telescopes all over the world in real time to Jive. So this is what our place looks like. Over here you have the machines with the disk packs processing. This is the central switching stuff. And this is where the operator sits. The disk packs get loaded and they run the processing. Our network looks like this. It's very simple. This is the central switch. Over here you have 1, 2, and nowadays even 3 times 10 gigabit to SurfNet. These are the 1 gigabit light paths that we have. As I said, 3 times 10 gigabit to SurfNet, 7 light paths, and we have 2 local links to a telescope in the Netherlands, which we use on CWM. So that's sort of our input networking capacity at this point in time. And then all the local equipment nowadays is connected over 10 GBT because that is so much cheaper. So there's 32 ports of that. And actually this picture is already a few months old. More things have already been connected again. A little overview of our network. I won't go through all the details, but we have connections that are, this is round trip time. We have connections that are long enough that it takes 1/3 of a second when you type something to get it echoed back. And we have connections that are much more local within the Netherlands, where it's within a millisecond. China, we have actually 2 ways of getting data from China to us. One of it is over a light path provided by Glyph, and that's the long way around that goes through Canada, basically. It's 354 milliseconds. We can also go over the Tyne network that's much shorter, but doesn't always have the bandwidth available. That's 180 milliseconds. Hard-based hook in South Africa. Just last month, we got a light path connected to that at 2 gigabits now. Arecibo, largest radio telescope in the world in Puerto Rico. We can at this moment do 512 megabit with them. Depending a little bit on the time of day, if people in Puerto Rico are awake, then we have to limit ourselves to 256 megabit, because otherwise we take too much of a chunk of the bandwidth that's available out of the island. And these are all telescopes in Europe that you could see on the very first slide. We do this quite regularly. About once a month we do real-time observations. And these are the results from the ones we happened to be doing last Tuesday. Well, these are not the results. This is the network throughput graph. So, as you can see, we run at about 6.3 gigabit for over 28 hours for this particular observation. And there's telescopes, Netherlands, Turin in Poland, Italy, the UK, Spain, Germany, Italy again. This was actually the first time that, sorry? You can get enough of one presentation of mine? Yeah, I can hear that. Thank you. Okay. It's actually the first time we had the Noto radio telescope in, which was a very nice first. It works quite well, as you can see. There's a few drops here and there where equipment crashes and needs to be restarted. These are all things that we are trying to improve upon, but it basically works automated for 28 hours now. So there used to be the Express project in which we pioneered the use of online real-time observations. And a follow-on on that is the project that we're busy on now, which is called NEXPRESS. It stands for Novel Explorations Pushing Robust VLBI Science. It's a 3-year project again, and we want to make VLBI a part of every VLBI observation. So at the moment we have sort of 2 worlds. We have the disk-based world where we get the data on disk, or we have the real-time observing. And we would like to combine the benefits of those. So in the NEXPRESS projects, there are many astronomical institutes and NRENs participating from all over Europe and even as far as Australia. It's an integrated infrastructure initiative, part of FP7, sponsored by the European Commission. So there's disk VLBI and there's eVLBI. And as I said, at the moment, there are basically 2 worlds next to one another. And we want to combine them. And why do we want that? If you record on disk, local at the telescope, it doesn't really matter how much network capacity they have. It goes on disk and we can just ship it later on. Whereas with eVLBI, some stations aren't even connected yet. Some only have like 60 or 100 megabit instead of the gigabit or higher that we actually would like to use. Shipping disks around the world, of course, takes weeks, especially if you want to bunch up a little collection of disks and send them at one go. Whereas with eVLBI, the data comes in near real time, and that has an important advantage because this is actually fairly complicated and many things can go wrong. A telescope can be a little bit off, a frequency can be a little bit wrong, atomic clock can be out of sync. All these things cause eVLBI or VLBI not to work. And having the ability to continuously in real time look at the quality of the data output makes the reliability much higher, because if data is shipped to us and we only get to see the quality of it later on, you basically can only decide to scrap the observation because you can't redo it. Because to redo it, you would have to re-record it with all the participating telescopes again. It has to be done in real time, in the same time, at all of them. So one of the limits we have is basically the logistics of our disk pool that we need to send to the telescopes and back again. It's about 2 petabytes of disks in these disk packs. Whereas with eVLBI, we don't need to store it on disks before we can correlate it. It basically goes over our network straight into the correlator and never hits a running disk until after it's been processed. That makes a number of very nice things possible. One of them is target of opportunity observing, where on very short notice we can actually bring the array live, which allows new kinds of science that weren't possible in the past because you simply first had to ship disks to the telescopes, and now it's actually possible we've done it within 48 hours already. Of course, with hard disks you have the problems that they occasionally break. So your data arrives at Jive and you plug in the hard disk and the hard disk suddenly starts emitting smoke. We've had a few of those. And then your data is gone. And of course, with networks as well, fibers can be broken. We've had backhoes. We've had ships that run their anchor through an undersea cable. Just this week, we had a train derailment somewhere in Europe that caused several fibers to go dark. So all kinds of problems happen with this as well. But bottom line is, with disk-based VLBI, we get better sensitivity, whereas with real-time VLBI, despite the fact that you can have network outages, we generally get much better reliability because we can do this online quality control. So what we want to do is the best of both worlds, eVLBI and VLBI combined. So this is sort of a schematic of how the setup works. We have an atomic clock at each telescope, a sampler that digitizes the data, and then nowadays either sends it to disk, and then we ship the disk and we play it back, or it plays in real time. But what we really want to do is is to do both. We want to record over here, so that in case somebody drives through the fiber, that we actually have a local copy that is guaranteed to be good. Then everything that we can send over the network, we will store over here as well. And as soon as it's safely over here, we can signal back to the other side that they can release the data. And we want to correlate it in real time so that we can see that the data has good quality. And then once we also get the data in from the stations that have lower network connectivity, we will then actually be able to rerun the correlation from local disk and get the best quality data. In the very first slide, I showed a world with all kinds of nice green lines, connections that we are able to use for our VLBI thanks to the help we get from many NRANs around the world. This is quite a large network, and it's completely static, because at the moment, setting up a light path is basically this. It is a switchboard. You call your NRAN, you said, I would like to have a connection from Holland to Puerto Rico, and then SurfNet calls someone in the UK, and they call someone in Canada, and they call someone in America, and they call someone in Puerto Rico. And after a long while, you have a light path that actually works very good. The traffic, and we need light paths because our traffic is constant rate, UDP, basically 1024 megabits per second, 24 hours long. Jumbo frames. We just keep pushing the traffic. We can't use TCP because over these very long links, if any packet goes lost, then we get TCP recovery and things just get worse from there on. And the other reason that we would like bandwidth on demand instead of static light paths is, well, we don't use these network resources all the time. Most of these telescopes are in other observation programs as well. They don't do VLBI all the time. We have 3 sessions that are each 2 or 3 weeks long, and we have our monthly eVLBI session, and in between those we don't really use the network. And the other thing is the actual network that we use changes from observation to observation, because sometimes we need different telescopes depending on what kind of frequencies they use, what location they have on the Earth, so that changes as well. At the moment we do 1024 megabit per second, and for most of the NRANs it's not really a very big problem to have a permanent 1 gigabit connection open for us. But we're also working very much on increasing the sensitivity and the bandwidth. And you can imagine having such a network with everyone at 10 gigabit or even higher would be more of a problem. So that's another reason for us to be really interested in bandwidth on demand. And that's also what got us involved in NSI, because VLBI happens on global scale, on intercontinental scale. So we don't just need the bandwidth on demand solution that is working for one provider. We need to go from one provider to the next, from telescope to correlator, and that usually involves several countries. So in NextPress there's one work package which I'm the work package leader for, which is called High Bandwidth on Demand, in which we work on these high bandwidth connections. There's a number of tasks defined in it. One of it is to actually integrate eVLBI with bandwidth on demand. So if we plan an observation, we should at the same time request our networking bandwidth so that it actually automatically comes up at the time that we start the observation. The second one is on-demand access for long-term archives. This is a work package being run by Astron. So apart from VLBI, which works at very high frequencies and works with dish telescopes, there's also a project in Holland called LOFAR, which you might have heard of. They also are pretty good at sending out lots of data. And they actually have long-time archives all over Holland and even over Europe. And they need to send data in between. And they would also like to make use of this bandwidth on demand protocols. The third task is testing and validation of these connections. Because it's very nice to have a 10 gig or a 1 gig connection, but you want to make sure that it works before you use it. So especially the University of Manchester, together with Jive, is developing protocols to test such a link before you actually trust it for using live data. And the last task is basically a demonstrator showing that we can do on-demand bandwidth at 4 gigabit or even 10 gigabit. For this, we've developed our own NSI client. So we actually have our own software that speaks the NSI protocol, and we go and talk to the OpenDirect NSI implementation at SurfNet, for instance, and said, we would like to have so much connectivity between these two ports on your network. And then we go and talk to Nordinet, say we want to have so much connectivity between those, and we stitch it all together, and then we have a path. And our client is made out of fairly simple things: Linux, Apache, PHP, where most coding is done, and MySQL. And the coding, by the way, is done by a gentleman over there, Fede, colleague of mine. He's done all the hard work. So this is our bandwidth on-demand client. And when we go into the language of NSI, we have a requester NSA, which send out requests, which get taken up by provider NSAs in the network, and they then give us the reservation we want. And that actually gets either changed through different networks, as Radek showed earlier, or at the moment that functionality isn't there with every NRAN. So what we also do is we go and talk to each of those NRANs, and we build the path we want, and we have the bandwidth available for our experiment. So the front end for it is a simple web browser front end. The backing store is MySQL. The things that we're still working on at the moment is to actually control our own equipment as well, because at this moment I simply log into our switch, set the VLANs, and have everything connected to the NSI. But what we really want is, once we get a connection up, is to also configure our networking equipment properly and in an automated fashion, so that we have an end-to-end system. And for that, we will actually use NSA ourselves, so we become a full provider as well as a requester. And that would also mean that people from somewhere else might be able to request bandwidth into our network if they have any reason to be there. This is a screenshot of our client. What you see over here is the STPs. These are the endpoints of a connection that we would like to stitch together. These are generally 2 ports on a particular switch, and you then know that one port is actually connected to a link to another provider, and one port is connected to us. So you go into the drop-down list, you select such a port, you select a time and date, you select the bandwidth, and you hit reserve and provision. And at that moment, the NSI state engine that Radek was showing us starts off and goes through several stages. And the first stage, I hope you can read it down here, is reserving, where all the NSAs are talking to one another, or we are talking to the NSA. And then at some point we get this message, we are actually in the state provisioned. That's the state where the network is there, where we can send data through it. And this is scheduled connection, so it also has an end time. So a little bit later, it actually becomes terminated again, and then the connection is gone. And so this bottom screen actually keeps track of our connections, and we can have multiple connections listed here while we go run an experiment. A recent demo we did, actually part of an Express deliverable, was to run 4 gigabit over an international path. So you're actually talking about cross-border, inter-domain bandwidth on demand, which is really the thing we are looking for in VLBI. So over here you have the Onsala radio telescope with a machine which is very boring name, Express. Goes through equipment at Onsala, then goes into equipment provided by Sunet, and then we go into Copenhagen, Nordinet. And I've actually colored these sort of by owner. So these blue ones are Nordinet, the orange ones are SurfNet. This is Jive equipment. And this map only shows basically what's needed to show the connection. And I know there's much more equipment involved in this than is actually on this map. But this is the equipment that actually speaks NSA. That's MX80 from Nordinet in Copenhagen. And over here, a SurfNet. This is a, what's the name again? A Force 10 switch in Amsterdam. And those are the ones we actually configure through NSI. And we know which connections are available in and out of them to then build up a path. So what we were doing is demonstrating 4 gigabits, and the result of that is a rather boring graph, which runs at slightly over 4 gigabit, because if you request 4 gigabit in iPerf, you tend to get a little bit more due to rounding errors. So 4.17 gigabit for almost an hour. there's 3 instances of packet loss, and they're just as likely to have been caused by the server being busy with something as actually having happened on the network. So it's not clear if there's any problem with the network. It worked exemplary. This is certainly the quality that we can use for doing VLBI on. We're not done yet with our NSI client. At the moment, we can make simple connections because the NSI protocol at this stage has a connection service. But there's much more happening in the NSI world, and we need to work on our client and work on the protocols to be able to make use of that. One of the interesting issues at the moment is path computation and path searching. So you have a topology, you want to go from A to B, you need to figure out which paths can I take and how can I request them and connect them together. The thing we're working on at the moment as well is how to manage our own networking equipment, and we try and do this in SNMP version 3 because we want to be able to manage many different kinds of equipment. The kinds of changes we need to make is we have to add a VLAN tag on outgoing traffic because we don't want to do it on the actual recorders. We want the network equipment to make these changes. And once you have a working path, you need to set up your routing both at the remote end and at our end so that the traffic actually takes this path. Because a light path goes between 2 ports on networking equipment, but generally there's more network equipment at an institute between the actual data equipment and the start of the light path. And we need to make sure that we can direct the traffic to go into the light path, pop out again at Holland, and then go into our equipment. The final goal of this whole project is that I get my schedule that lists which telescopes are going to observe at which time, at which bandwidth, parse it, create a schedule out of that that tells me which connections I'm going to use, and the software should automatically reserve the paths that we need, warn the end user if the paths aren't there or aren't possible, and then just have the reservations basically made as far in advance as that we know that we will have telescope time. And another deliverable within our project is to integrate the reservations with actually testing the link and then bringing it down again and bringing the link back up when we actually run the observation. And that's also has some very interesting issues because that you want to be sure that the link that you're testing is actually going to be the link that you're going to use in the end. And it's not even clear at this moment whether NSI will support such a use, for instance. And then on my final slide, the things that we hope to do in the shorter and the longer term future. Actually, on the 20th of June, we hope to have our very first observation at 4 gigabit per station. Some of that connectivity is going to be routed. Some of them might be over bandwidth on demand. It's going to be 3 stations in there. Yebes in Spain, Onzola in Nordinet, and Effelsberg. Later this year, also as a deliverable within Express, we're going to be trying the very first 10 gigabit international bandwidth on demand. We also want to be able to use our NSI client, not just to talk to Nordinet and SurfNet as we've done so far, but also to start talking to Autobahn, resources to Glyph, to other NRANs. We're also working on getting the LoFar 10 gigabit archive interfaces working. That's mostly going to be within the Netherlands at first, but that also is going to be international because there's archive sites in Germany already, possibly in France. And as I said, the final goal of the final deliverable for the Express project is to integrate the NSI client with the scheduling for radio astronomy, have an integrated overview, click on a button, have your light paths reserved, do your observation, release the resources again so other people can use it. Thank you.
Thank you, Paul. I can see a question already, so please go ahead.
Hi. Do you have an idea how you will do the path calculation? So on which data you will work?
Well, the topology within NSI hasn't quite been defined yet, and I already see the next speaker getting up. Our thoughts at this moment are you could have a static topology, so you don't actually know how much bandwidth is available. In that case, you simply do a standard Dijkstra shortest path first, and then you try and reserve that bandwidth. You try all the links, and then if you find out that a particular link is unavailable to you, oversubscribed, you excise that particular link from your topology and you try again. Another possibility might be that actually the topology is much more dynamic and actually knows how much bandwidth is available on each link. In that case, you could do the topology in one go, or sorry, the pathfinding in one go. But are you going to talk about this? Yes. Okay, then I won't say any more about that. Thank you.
Thanks, Sarah. I can also talk about the answers on pathfinding, so I won't do that. So I'll just ask a brief VLBI question. You mentioned that in one of your slides that disk VLBI has higher sensitivity than eVLBI. And
yes.
Also you mentioned that the higher the bandwidth, the higher the sensitivity.
Yes.
Could you just increase the eVLBI sensitivity to the same level as a disk-based VLBI? And if so, how much bandwidth would you need?
Yeah, right. The limitation in sensitivity for eVLBI, for network-based VLBI, is simply the fact that some telescopes aren't even connected, so we can't use them in real time. And some of them have a much smaller connection than what we actually need, because the high sensitivity observations we do, we run at this moment at 1024 megabit per station. So if a station doesn't have that much connectivity, what we end up is throwing away some data and losing some sensitivity. So yeah, as soon as every station, and that includes stations in Siberia, for instance, as soon as all these stations have 1024 megabits, then the bandwidth would, and the sensitivity would be comparable. And of course, we are actually working on increasing our bandwidth. For a long time, 1024 has been our limit, but we are now working on our first 4 gigabit test, where we have twice the sensitivity we had before. Thank you. Okay. Got time for another one?
Just one quick question.
The power of 2, 1024, is that an application-specific choice?
No, there's actually something that still comes back to when we were doing this on tape. The tape speeds were powers of 2, where you used twice the number of tracks on the head of the tape, and then you had a higher speed. It started with a megabit and just went in powers of 2 from that. And at some point of time, that actually led to the very unfortunate situation that the highest speed that we could do was actually slightly higher than what you can get through a gigabit Ethernet. And that caused quite a few headaches for us and for the networking providers. We are no longer using tape-based formats. We are no longer using data acquisition equipment that still stems from that date far in the past. So we're getting much more flexible about that. So the 4 gigabit I'm talking about is actually 4 gigabit and not 4096. Okay, thank you.
Great. Well, thank you. Thanks again, Paul. It was a very good talk. So our next speaker is Jeroen van der Ham. Jeroen is working at the University of Amsterdam, and he's specialized in his PhD and his other research in modeling networks. So as has been discussed in the presentation so far, we're trying to solve a problem of a multi-provider environment. These providers have a topology of different components in the network. How can you model those that network and then exchange that information so that everybody has a clear understanding of what the network resources are? So that's the topic that Jeroen will cover.
Thank you. The presentation that I'm about to give is a cooperation between Jerry Sobieski, who works for Nordnet, and myself. The roles that he gave us is not something that I invented, but that he put on the slides himself. So the basic thing about the NSI is that we need to have or that we're providing a network service. In order to do a network service, you need to have some kind of view of what the network looks like before you can actually make connections across them. In the version 1.0 of the NSI, the network service interface, we've been using a static topology, which is pre-distributed to all the participants in the testbed. And in the next version, we're thinking about making a topology distribution mechanism. Once you start doing the topology distribution mechanism and the topology representations in general, you have to think about how to represent those networks. And the big question of this presentation and what we're trying to figure out right now in the network service interface working group is what is the proper strategy for making detailed internal network topology information publicly available to a global user community, so that they can actually do pathfinding with it in a way that is useful to them and feasible. We will look at this from two different perspectives: a default open detailed topology, so everybody knows everything about all networks, and the other end of the spectrum, a very limited services specific topology only. Well, why do we need topology? We need it for the service provisioning. In order to do routing, connection path planning, traffic engineering, you need to know what the network looks like before you can actually make a request from one point to another. Once you have the request, you need to be able to figure out which of the domains that you need to do the actual planning or to do the actual requesting of all the segments that you need. Once you have a path in place, you need to, the knowledge of the topology is very useful if you want to do service debugging and fault localization, so that you can figure out where the problems are, who you can contact about the problems that you have, and possibly that you can route around it. So for resiliency and robustness, you need to have know what other possibilities are open to you to do the to plan alternatives to your own circuit. And as Paul already mentioned, you need to know where you can actually go with your network, and what the capacity is that can get you there. What constitutes topology? So it's any information that you need to make to make decisions about where you want to go from one point in the network to the other. You need to know about the resources in the graph, so the points and how they are connected to each other. This is not just servers and links, but also the technologies that connect them together and the capacities that are in there. But that's just the basic thing about the topology. If you start thinking about inter-domain topologies, then you need to know adjacencies and grouping. So how are things grouped together in a domain? How are domains connected to each other? Then if we start looking into making reservations, then all of a sudden you need to know what state the network is in. Is the connection that you're looking for, is it actually available? And is it available in the time that you want it? So there's another dimension. And then there's all the functional components. What is the networking technology that is connecting those two things? And how does that allow you to transport your whole data flow through the whole network? This already gives you, so the topology is a very big, complex and dynamic thing. I mean, you have a lot of different networks that are connected together with a lot of different components, and you have the state information in there. If you think about the RNE networks that have a very high number of physical network elements, which then have a very high number of ports, not all of these are, of course, for circuit-based network provisioning that we're looking at right now, but many of them are. And then if you add to that you can also have virtual resources, then we have multi-layer technologies. There's DWDM, there's Sonnet, there's VLANs. Each of those adds more complexity, more labels, and more topology information than on what is available and what you can do with the network. And then for each of those elements, you have to have the state of the network in order to think about what is available. And if you then start distributing this globally between all these domains with many different decision points, it's a very big and very complex problem. So it's very relevant that we look at this. The scheduling of resources adds another dimension, because there's also the policy involved. NRENs usually have a very open mind about scientists using the network topology or the network resources. If they ask, then there's a very big chance that they can use it. But there's a policy giving access to the users, and they have to authenticate themselves. We have to think about a way to represent when users can access certain resources, how you can represent that decision model beforehand, so that you make it clear to users whether they can access certain resources or not. The other option is that they just come and ask you each time. That may scale for some time, but in the end, if the circuit-based networking takes off, then you're getting requests a lot. Then, so for pathfinding purposes, if you look at a resource in the topology, the availability means the performance that's required by the user, the time that is needed, and whether it's actually available to him, to that specific user. So that has a lot of different dimensions for the availability. If we look at the way that you can do pathfinding, there's two different approaches right now. You can go, if you want to make a reservation from A to Z, you can go through each of the networks and look at if you can get a certain segment, then you look at the next segment, then the next one, and then you figure out that you found the path to the end, and then you can start reserving it all at the same time. Each sends a confirmation back that the circuit is actually available, and then you have a complete path. So you first select the network, and then you make a reservation. The other option is that you do it hop by hop. You select a certain path through the network, you reserve that path, and then you go on to the next one and you make a reservation and you go back, and then you go to the last one, you make the reservation and you go back. This is a slightly different approach. Both are supported by the NSI protocol. I'm not completely sure whether the current implementations support both of them, but in the end, this is what we. This is two different uses that can happen. The considerations for this is that if you look at the previous path, you were doing it in a hop by hop fashion. It can turn out that one of the segments is not available, or say that this one is not available when you're doing the selection. Then you can do something that's called a crankback, and you go back to the previous reservation and try to find an alternative for the path that you were taking, and then you still keep your previous reservation, and you go back and follow a different route and continue with the reservation. If that also fails, then you go back to another step and try to figure out what another alternative might be. The second thing is that pathfinding may be recursive. The pathfinding itself, this is a global view of the topology, but it may be that this domain actually is giving you an abstract representation of the network, and internally it may do another pathfinding. So this domain may represent a very large group of resources, and internally they do pathfinding as well. This limits the complexity for the end user to doing the pathfinding at first. So the selection of a path is based upon the user constraints. The user provides the constraints, saying he wants the path for a certain time with a certain bandwidth, and based on the endpoints, there's also a certain kind of technology involved to transfer the data between those two endpoints. How much of the constraints can be expressed by the user and how they can be managed by the pathfinding agents also depends on how much can be represented in the topology itself. So how much detail is provided in the topology gives users the ability to make more detailed requests. The details, of course, need to be passed on through each of the agents involved in the whole path planning process. In the NSI, we believe that the pathfinding and the path planning should be requester based. So the decision should be with the requester instead of the provider. The current NSI implementation gives the user the ability to figure out the path before requesting it, and then going and requesting each of the segments that's needed, and in that sense making the decision himself. And the other option is that the requester goes to a provider and says, I want to have a path from A to B, and then the provider just gives him a path. But on the other hand, if you give users this amount of freedom to select a path through the whole network, then it becomes very hard for the networks to manage the resources and to distribute the load through their network in an equal way, so that other users are not affected by these kind of connections. So we need to find a balance between the minimum amount of topology announcement that the providers give out, but it shouldn't be overly paranoid. It should be encouraged to announce topology where it poses little to no threat to operational stability. It's not always the case that giving out information about your network is dangerous. But then again, it's very hard to strike the right balance. You can look at the Nordinet network, or the Northern Light goal, which has connections to Amsterdam, the UVA, Poznan, and at the other side of the Atlantic to Chicago, Washington, and Starlight. But you can look at that also with the MPLS infrastructure, which is a lot more complex, but it still contains abstractions. We can make this even more detailed with including the SDH layer, but this still contains some, and the dark fiber, but this still contains some abstractions about how the circuits are provisioned. But the question is, do the requesters actually need that kind of information to do the path planning that they need? So, on the one hand, you do want to give them enough information to make paths to make useful path requests that they need, but on the other hand, you don't want to give them too much detail that they don't really need. In the other sense, there's different approaches in doing topology aggregation. If you have a full view of your network, you can aggregate that in different ways. You can just say, my network is a single point, and I make it very easy for you to cross my network. Or you can give them a full mesh view of your network. This abstracts away some details, but still gives them information about the availability of the connections between the two border nodes. Or a middle ground is a star network where you have a center node and spokes to the edges, which gives you some idea of the availability of the network, but still hides some of the complexity of the network itself. But this does have implications on how, on what you're actually promising the user. If you're broadcasting your network as a single point, then you're basically saying that your internal network will never be a problem in crossing, because users expect if they come in here and they go out there that this will always be possible, because you're not advertising that there is a line there that can be blocked. So we have the open topology, which allows users to do optimal path calculations in end-to-end multi-domain scenarios. They have detailed access to all of the details that can be important to fault localization and the mitigation. The technologies involved, so they can actually understand what's going on when their bytes are being transported from one point to the other. But the risks are that there's security and privacy. For the network providers, it may not be it may not be secure for them to give out the whole detailed plan of their network. And if you're giving your users this kind of detail, it also gives you reduced flexibility on what you can do with their requests. If they specifically say, I want to go through these nodes here through your network, and one of them breaks, or you want to do maintenance on one of them, you can't just take it out, do a hot swap, and make it cross some other path, because it affects how they see the network. If you're not giving out those details and things change, then they may not notice, or they may not care even, and then it gives you more flexibility. For the users, the downside of a very open topology is that it's a complex, massive, dynamic heap of information that you're exposing them to. Network topologies are very complex, is what I said. There's different technologies, there's different availability rates, and pathfinding across these kinds of topologies is actually an NP-complete problem. So it's very hard to do the pathfinding calculations. There are many. Most of the users for bandwidth on demand don't really care about all the details. Many just want to have a connection from one point to the other with a very high amount of bandwidth. Others may be more interested in having a low delay kind of connection, and in that sense they do care about, well, the details of the technology. The authorization policies are very tricky to represent and to describe, and then to distribute also. On the other hand, if you do give out open topology information to all your users, you're giving them free range to do with the network whatever, well, not whatever they want. I mean, there's still the topology or the policy involved, and you're still, they still have to make the request, and you have to approve the request. But they can engineer their own virtual network that crosses multiple domains, and they can do it in a way that they specifically want, which allows them to do more sophisticated end-to-end services. For the NSI framework is intended to be an inter-domain environment. The path selection is done inter-domain, and then each of the domains implements implements the path as a hop-by-hop basis. The path planning is done by the local NSA, or the one that is coordinating the whole request, which can be the user if he wants to. But currently, the domain level summarization hides some path planning options. The NSI networks are assumed to have a monolithic service region, so they all have the consistent capabilities. We're currently looking at a more sophisticated topology architecture that can distribute more information across all of the different NSI agents and to the users as well. But this is something that we're implementing right now in the, or describing right now in the NSI 2.0. So, what I've been describing is that or what I'd like to try to get across is that topology distribution and topology description is still a very complex problem. We're looking at the issues involved. We have some ideas on how to solve them, and in the next few months we're going to describe this in the NSI 2.0 document. Then we're going to work on the implementations, and then we'll see what will happen.
Okay.
Questions?
Nice. Questions.
For me, it's not clear. How do you choose the best paths? For example, if you have two options from A to B,
yeah,
which one do you choose? What are the what's the metric?
That's what is the metric is actually, that's a very big problem. Right now there's no, the NSI does not impose a metric. We're just giving out the topology information, and then we allow you to choose.
Yeah, but you need this because the best path selection needs a metric.
Yes.
The first one. Okay.
Well, the Dijkstra needs a metric to make a shortest path decision. But right now, if you're doing the interdomain circuits, then it may not be that you actually require the shortest path. It may be that a longer path also suits your needs.
Yeah, it's a definition. What's the shortest path?
Yes.
It could be of course, the amount of bandwidth or the round trip time.
It depends on the constraints that you put on the request, what the best path is going to be for you. It may be that it's the shortest one, or it may be that it's the one with the highest bandwidth, or the one that uses certain kind of technologies.
How is this done in the current testbeds?
The current testbed still has a single technology domain that uses the basic Dijkstra planning. but we've been working on the...
So you use the shortest path with the hops?
Yes.
Okay.
And who will keep all this information about the potential nodes and the passes? And who will create this information, database of information about potential topologies which would be selected by the NSI or what?
So the whole architecture right now is that there's that there are multiple agents involved, and they exchange the topology information between them. So they all build up a view of the whole world, and then the one that you submit a request to is going to do the path planning process, and that one selects which paths are available and how to proceed with the path and which candidate to select if one does not work.
Okay. But you don't want to assume that you want shortest path as the metric, especially not interdomain. In some cases, you might want to distribute the usage of the resources more evenly. In other times, in fact, there's talk of going green and concentrating the use of resources, leaving some of them fallow, et cetera.
Yes.
So I really liked the very first question, which was, what is the metric?
Yeah, the metric, it's like I said, the metric's going to be what is going to depend very much on what the user selects as constraints. And the domains, of course. But that is on the providing side. So the metrics that the users can select and the constraints that the users can select depend on what kind of information the domains actually provide. If you're not giving out information about your energy consumption of your network nodes, then I can't make any decisions on the best green path. So it's a two-part problem.
So I think you have to agree on attributes of a path, and then it's up to the user to define his own metric, and it's up to the participating networks to, if you will, define a matrix of from among all the entrance and exit points, what the attributes are on every possible path, and leave it up to the user to decide.
Of course.
You don't need to publish the entire internal topology, internal characteristics of your network. That will never happen. All you need to know are input to output.
That's not necessarily true in multi-domain networks. In multi-domain networks, I mean multi-layer networks, it's going to depend on the technology that you use to transport your data across the network. Then it may also be relevant on what kind of adaptation you use to go from one technology to another. There have been cases that the way you transport the gigabit Ethernet over a SONET is incompatible, and you need to know how you got to that transportation layer and how you can get back out. So that kind of information may also be relevant. It's another attribute, yes. But it's very hard to say beforehand which attributes are necessary in order to do the calculations. Then again, I mean, we are working in a standardization organization to make a standard way of describing the networks, describing the capabilities of all of the networks, so that you can actually make these kind of decisions, because otherwise it becomes a free-for-all, and then nobody can make paths.
So it seems to me that what has to happen is that when a user makes a request and the agents start looking for the potential intermediate networks, that they're going to hand the parameters of the user request to the intermediate networks.
Yes.
And the intermediate networks are going to make the decision as to what path they will allow. And I would guess very strongly that in many cases there are not going to be a lot of options. That is, the intermediate network will look at its current topology, its current loads, its current commitments, and it will return a very small number of choices for the possible paths, even smaller given the fact that there may only be a one or two connections between these intermediate networks where you could actually formulate a path at all.
Yeah, that's true. But on the other hand, you're going to have to make trade-offs somewhere, and it may be that the user prefers certain trade-offs above others. So. Do you think about backup path, for example? Yeah, a backup path is also it's another kind of constraint that you can put on your pathfinding problem. If you want to have a backup path, then you can look at the topology, try to make a backup path that is as much different from your current path as possible. But that may not always be possible.
Okay, I'm conscious that we're sort of come a little bit beyond our time, a few minutes over. And perhaps that would be a good point to wrap up. Do you have any more comments? Any last-minute questions before we wrap up? Okay. Just to review really where we are with NSI. We've had 3 great presentations. We've had Radek's introduction to the concepts. You know what NSI is. It's a protocol, a connection service that allows multi-domain provisioning. We've had a great use case there from Paul, which gives us a fantastic example of why it's necessary. And then we've had some really stimulating intellectual problems about the trade-off complexities in topology modeling and exchanging those topology models, and how do we actually do pathfinding on that? Is it a scalable problem, and how do we solve that? So I'd like to thank you all for your participation, your great questions. I hope it's been a good session for you all. Thank you.